Welcome to Maths with EJD. In this video, I'll be talking about limits of functions and continuity. Of course, I've talked about this under basic calculus. We are looking at it from the angle of real analysis, where we get to talk about things like delta epsilon or epsilon delta proofs. So let's go for that right now. So limits of functions and continuity. Okay, when we talk about the idea of a limit, one practical example that we can think about is you walking towards a wall. Maybe you are in a place and there's a wall ahead of you. So as you get closer and closer to the wall, we can say the wall is like a kind of limiting, it's a barrier, right? So, but you can walk towards the wall from one side. You have a wall, right? So you can walk towards the wall from one side or another side, right? So there are two sides to every wall for sure. So you can walk towards the wall from a side or you can walk towards it from another side. And that gives us the idea of limits. So when we talk about one-sided limits in that regard, then that's the analogy I just gave now. So the right-hand limit is, of course, we're talking about function, right? So you have a function f of x. So the right-hand limit of that function is of the limit f of x, of the limit of f of x rather, is the limit of f of x as x approaches a plus from the positive side, right? So I mean, as x approaches a from the positive side, so imagine that let's say the limit is zero, the limit of a function. If you take a value zero, that's where the wall is at, so to speak. So you can approach zero from the positive side. Maybe you're coming from +10, +9, +8, +7, then you get to +2, +1, then you get to zero. Or you could be coming from the negative side, that is -10, -9, -8, -7, and then you get to -2, -1. So you can approach the limit from two sides. So generally speaking, that's what we talk about, one-sided limit. So the right-hand limit is given as limit of f of x as x approaches a from the positive side. And the left-hand limit is limit of f of x as x approaches a from the negative side. In that case, having seen these two-sided limits, then we can say that a two-sided limit exists if and only if both one-sided limits exist and are equal. So it means that for a particular, for you to say something has a limit, it means that the two-sided limits, the two one-sided limits, that is the right-hand limit and the left-hand limit, must exist. They must be defined. And after being defined, they must be equal for you to say that the function f of x actually has a limit. Of course, in a broad term, you can say it has a two-sided limit or simply a limit. So no function has a limit unless it's two one-sided limits, that is the right-hand limit and the left-hand limit exist and they are equal. Basically, that's what that is about. And let's talk about the algebra of limits. I think we've seen things like this in a previous video. So if you imagine that the limit of f of x as x approaches a is equal to L, right? And the limit of g of x as x approaches a is equal to m, then we can say that the limit of f of x plus g of x as x approaches a is simply the sum of the the sum of the limits of the two functions. So in essence, we are saying that the limit of two functions is the sum of their limits. The limit of the sum of two functions, rather, is the sum of their limits, something like that. And then here you have the limit of as x of f of x times g of x as x approaches a is equal to Lm. That means that the limit of the product of two functions is the product of their individual limits, right? As you can see. Then we have the same for the quotient. So the limit of f of x over g of x as x approaches a is equal to L over m. Of course, that limit m must not be equal to 0. So in essence, you're saying that the limit of a quotient is the quotient of the individual limits of the functions involved, like that. So that talks about the algebra of limits. And then that takes us to the idea of continuity. Okay, we go to the idea of continuity of functions. Okay, let me just focus on this first. Okay. So talking about continuity of functions, we say that a function f is continuous at a, given three conditions. First of all, f of a is defined, that means the function is defined at the limit, at the value towards which the independent variable x approaches. So it must be defined at that point. Another thing is that the limit of f of x as x approaches a must exist, meaning that the limit as x approaches a plus, the limit as x approaches a minus, both exist. So that means the limit of f of x exists as x approaches a. Then lastly, both the limits of f of x approach as x approaches a and the evaluation of the function at a, both of them exist. So we are saying we have point 1, point 2, and point 1 must be equal to point 2. So condition 1 and condition 2 must be equal. That's the third condition. So that way you can say that a function is continuous. And then, of course, it means that there are cases if any of this breaks down. For instance, if f of a is defined and the limit of f of x exists, but they are not equal, then the first two conditions have been met, but the third one has not been met because the two conditions are not equal. So in that case, you can say the function is discontinuous. And then we have different types of discontinuities. We have what you call a removable continuity, where in a case, for instance, you have like f of x equals sine x over x at x equals 0. So at x equals 0, you have a removable discontinuity for sine x over x. And what happens in that case is, of course, sine x is 0, and that is not the problem. The problem is that the denominator is 0, and you cannot define. If you divide by 0, it will be undefined. So it means that you have a removable continuity at that point in time. Then you have a jump. You can have a jump, which is also a discontinuity. For instance, if you have f of x equals sine of x, that sign now is SIGN. So maybe it's plus or minus, right? So at x equals 0, x is neutral. So, I mean, 0 is neutral, by the way. So if you are going on the negative side of things, once you get to 0, you automatically just jump to the positive side, as you're going to see very soon. So in that case, we have a jump for f of x equals SGN of x, where SGN simply just talks about the negative sign or the positive sign. And at x equals 0, being a neutral value, you have a jump at x equals 0. And then you have what you call an essential discontinuity, where you have a case like that for f of x equals sine 1 over x. So at x equals 0, sine 1 over 0 will be sine of infinity. And sine of infinity is chaotic. So around x equals 0, you have the function misbehaving. It becomes pretty chaotic. So let's look at some of these concepts in more depth. So let's look at the concepts of those types of continuities. So here are the definitions of each type of discontinuity. We have removable discontinuity. It's a discontinuity at a point A. A continuity at a point A is removable if the limit of the function as x approaches A exists, right? But either the function is not defined at A or so for sine x over x, now you can see the function is not defined at 0. So in that case, our A is 0, or the function's value at A is not equal to the limit, right? That means that the condition for continuity is not satisfied because the function evaluated at A exists. The limit as x approaches A for f of x is actually exists too, and the third condition is that they are equal. So maybe the first two conditions are okay, but the last condition is not met. That's another case where you have removable discontinuity. So this type of discontinuity can be removed by redefining the function at that single point to be equal to the limit, right? So then we have a jump discontinuity, which is a discontinuity where the one-sided limits exist at a point A, but they are not equal. So you have a jump at that point. So so just like the case of SGN of x, right? So at the negative side, the numbers approach 0, and at the positive side, numbers also approach 0, but the values are not the same, right? So, and that is why you have a jump. So a discontinuity where the one-sided limits exist at a point A, but they are not equal. The function jumps from one value to another at that point, right? So you have essential discontinuity also, so which is a discontinuity at a point A where at least one of the one-sided limits does not exist. Either it is finite or infinite. The behavior of the function is often erratic near the point of discontinuity. That's why I said things can get chaotic. So to demonstrate that now, I have this Python code to show, for each of them. So the first one is for removable discontinuity for something like sine x over x, as you see in line 9. Okay, of course, we are using matplotlib and numpy for removable discontinuity. We define a function, removable discontinuity. If x is 0, then return none. That means it is undefined at x equals 0. Else, return np dot sine x over x. And then for x removable, you have -5 to 5. So between -5 and 5, there's 0 right there. So you're definitely going to have a point of discontinuity at 0. And of course, you are doing 200 divisions of between -5 and 5. Now for the y removable, now, so you have removable discontinuity xi for xi in x removable. So of course, this is to show us the graph because you are plotting x removable against y removable. So I run that now. We'll see what that gives us. Of course, this is the first code I'm running in this session, so it takes a bit more time. Okay, so there we have it. So you see, we have a removable discontinuity around this place, right? So of course, everything still looks okay, but that's not the ideal, right? Because at 0, right, everything still appears smooth, but that's not the reality that should be happening right there. Uh, because we can still find continuity in the sense that if we have sin x over x at 0 doesn't work, but if we use L'Hopital's rule, for instance, we have cos x cos x all over 1 and cos 0 is 1. And that is why we have this value. So that's a removable discontinuity at x equals 0. Okay, then we also have the next one, that's a jump discontinuity. So for the jump discontinuity, so then you're going to see a jump. So we have from -1 to 1 in 200 divisions, we have essential discontinuity around x equals 0. So here now we do the same, but then we're talking about sine 1 over x. And then we are plotting x sorry, I jumped this remove a jump. So we're talking about jump discontinuity, talking about sine function. So for sine function now, if x is equal to 0, it returns 1. So it is approaching 1 here. So else if x is less than 0, it approaches -1. Else you return 0, which can be undefined, right? So you have that jump at 0. So if you run this now, you can easily have that jump discontinuity. So you can see that as x is approaching 0, we keep going like that. So, I mean, we have -1. So we have -1 maintained all the way. But when it is -1 all the way, but when you get to 0 here, you have a switch over to this. And that's why you have at 0 now, there's a jump like that. That's jump discontinuity. And for essential discontinuity, you can see around x equals 0, you have a kind of chaos happening around here. So things are hardly defined around that. And that is the idea of essential discontinuity. So the next thing now, let's talk about composition of continuous functions. Okay, if f is continuous at a and g, if f is continuous at a, right, and g is continuous at f of a, so then g of f is continuous at a. So we are saying that if a function f is continuous at x equals a, and a function g is continuous at the same f of a, so it means that you can have the function g can be, if you compose g with f, that's g of f of a, or g of f is continuous at that a. So that's basically the idea of composition of continuous functions. Now, if you want more, if you want to see numerical solution kind of approach to this, you can check my playlist on basic calculus, where you get to see functions. So let me check that now. So I think I have a video there on operations of functions, things like composition, inversion of functions, and things like that. Okay. So I'll just go straight to, okay. Yeah, so it's better to see from playlists. Yeah, so Basic Calculus was one of the earliest playlists on this channel. Yeah, right here, 26 videos. Yeah. So we have operations on functions of real variable. So here you get to see things like composition of functions and things like that. So this deals with that idea. Yeah, so you can see composition right here. So composition of functions of real variables. So you want to check the second video on the basic calculus playlist. So that gives more light on this idea shared here. Okay. So let's talk about a kind of introduction to uniform continuity, right? So here we say that if a function f is defined such that A belongs to the real number system. So f defined from A to R is uniformly continuous on A, right? It is uniformly continuous on a set A. So if for all epsilon greater than 0, there exists delta greater than 0, such that the difference between x minus y is less than delta, implies that f of x minus f of y is less than epsilon for all x and y belonging to A. So in this case now, that is what we call uniform continuity. So we say a function defined from a set A to the real number system is uniformly continuous on A if this condition is met, that for all epsilon greater than 0, we have said already that epsilon and delta are very small numbers greater than 0, maybe things like 0.00001 or something like that. So for all epsilon greater than 0, there exists delta greater than 0 such that the absolute value of x minus y less than delta implies that the absolute value of f of x minus f of y is also less than epsilon for all x and y belonging to the set A. So unlike pointwise continuity, so this is uniform continuity now. Unlike pointwise continuity, the delta depends only on epsilon and not on the point, right? So for pointwise continuity, delta depends on does not depend only on epsilon. Okay, so a preview will be by the Heine-Cantor theorem. Every continuous function f on the closed interval AB is uniformly continuous. That's what the Heine-Cantor theorem states, that every continuous function, so once a function is continuous on a closed interval AB, then we can say that it is uniformly continuous, right? And then we go for the sequential criterion. Sequential criterion. So this one talks about the fact that the limit of f of x as x approaches A is L, right? If and only if for every sequence xn with xn approaching A and xn not equal to A. Of course, in the idea of limits, right? Xn is approaching a value, but it doesn't ever get to that value. That's what limit is about, right? With xn approaching A and xn is not equal to A, then we say that the limit as n approaches infinity of f of xn is equal to the same L. So in essence, we are saying that if f of x is equal to, if f of x has a limit, basically, if f of f of x has a limit, then for so okay, we say that the function f of x has a limit if and only if the sequence xn also, as n goes to infinity, also has a limit. So that's the idea. So continuity at A is equivalent to the fact that xn approaches A, then f of xn approaches f of A. That's the kind of idea we have in this situation. So sequential criterion. So sequence as a criterion for a function, that's the kind of thing. So, and of course, if you have to prove something like this and only if condition means that you have to prove that f of x has limit L, given that f of xn has limit L. Then you have to prove it backward. I mean, f of x has limit L as x approaches 0, given that f of xn has limit L as n approaches infinity. Then conversely, you also have to prove that that f of xn has limit L as n approaches infinity, given that f of x has limit L as x approaches A. So you have to do it in two ways. So anytime you see if and only if, it means you have to prove in both ways. So we have uniform continuity on a closed interval AB. So a kind of preview on that now. Okay, so here we have this uniform continuity on closed interval AB. So if f is continuous on the closed interval AB, then f is uniformly continuous. I think that was what we saw for the what I think we saw something the Heine-Cantor, yeah. That's the Heine-Cantor thing coming up here again. So if f is continuous on closed interval AB, then f is uniformly continuous. So the idea is that AB is compact, and then continuous functions on compact sets are uniformly continuous. So every continuous function on a compact set is uniformly continuous. Then the full proof can come later, and it requires the Bose-Weierstrass theorem, which we had seen, I think, in a previous video. Then the next thing, let's talk about rational and irrational based functions. Define, for instance, a step function. This is called a step function. A function that has different values within different limits is called a step function. Imagine that f of x is 1, given that x is a rational number, and then f of x is 0, given that x is not a rational number. That is, x is irrational. So this is called a Dirichlet function, and it is discontinuous everywhere, right? So it is discontinuous everywhere. Now, so it means it is discontinuous everywhere. But when we have h of x is equal to x, when x is rational, but h of x is 0, when x is irrational, then we say that this is continuous at 0, but discontinuous elsewhere. So it is continuous at 0, but discontinuous elsewhere. Okay? And then that takes us to the concept of epsilon delta proofs. I think this is the highlight of anything about limits and functions in real analysis. The epsilon delta proofs are like the big deal. So because if you look at the basic calculus video playlist I showed you before, if you get there, we are showing limits numerically, right? But for epsilon delta proofs, we are using pure abstract logic, right? So the epsilon delta definition of a limit is a rigorous way to define what it means for a function to approach a certain value as the input approaches a specific point. So the definition states that for a limit, limit f of x as x approaches 0 equals L to exist. So for f of x to have this limit L as x is approaching a, for that to exist, right? For every epsilon greater than 0, epsilon here representing a small positive number for the desired closeness of f of x to L. Okay, there must exist a delta greater than 0. Same thing, delta representing a small positive number for the required closeness of x to a. So, epsilon is close to f of x, while delta is close to a, towards which x is approaching. Okay, such that if the distance between x and a is less than delta, but not equal to 0, so it's a very small gap, then the distance between f of x and L is less than epsilon also. So that's the foundation of epsilon delta proofs, right? So you have okay, of course, the math is next. I think I should just go for that straight. So in mathematical notation, all we have just said now is that all we have just said is basically this, that for all epsilon greater than 0, there exists a particular delta which is also greater than 0, such that the absolute value of x minus a lies between 0 and delta, and that implies that the absolute value of f of x minus L is less than epsilon. That's basically what all of that story we have told. That's what it means mathematically. In simpler terms, right, no matter how small you make the interval around L, defined by epsilon, so you can always find an interval around a defined by delta, such that for any x in that interval, which is x, except possibly a itself, the function value f of x will be within the epsilon interval around L. That's another way to look at it. So epsilon delta proofs involve starting with an arbitrary epsilon greater than 0, and then finding a delta which usually depends on epsilon that satisfies the condition. So absolute value of f of x minus L less than epsilon whenever absolute value of absolute value of x minus a lying between 0 and delta. All right. So the key is to manipulate the expression f of x minus L to reveal a term involving x minus a, and then use the assumption f x minus a less than delta to show that absolute value of f of x minus L can be made less than epsilon. Okay, so in essence, let's see. Okay, so I'll just explain. I'll explain the first one verbally. I'll explain the first one just like that, and then the second one I'll try to just work it out, right? So prove the limit of x limit x squared as x approaches 0 equals 0. Then we want to show that. So what we want to do here is I want to show that for every epsilon greater than 0, there exists a particular delta greater than 0, such that if 0 is less than the absolute value of x minus 0. So now x now is approaching 0. So that's why instead of x minus a, we have x minus 0, and that is less than delta. Then the f of x itself, which is x squared minus 0, is less than epsilon. So all we just now need to do is to work on this x minus 0 part until we get to work on this x squared minus 0, right? Until we get x minus 0 in between. So in essence, we have absolute value of x squared minus 0 equals absolute value of x squared, of course, and that is equal to absolute value of x squared. And then at the end of the day, we want absolute value of x squared to be less than epsilon, right? So if we take the square root of both sides, we get absolute value of x is less than square root of epsilon. So if we choose delta is absolute value of epsilon, square root of epsilon rather, then when 0 is less than absolute value of x less than delta, we have that absolute value of x less than square root of epsilon, which implies that x squared is less than uh, uh, square of the square root of epsilon, which is simply epsilon. Thus, for any epsilon greater than 0, we can choose delta, which is equal to square root of epsilon, and the condition is satisfied. Therefore, we can conclude that the limit, right, that the limit as x approaches 0 for x squared is equal to 0. Okay, so let me try to take that to a worksheet, and so I'll try to do the second one on a worksheet following that same argument. So our job here is to prove that limit as x approaches a of 2x as 2x plus 1 limit of 2x plus 1 as x approaches a is equal to 2a plus 1. So that's basically what we want to do. And then how do we do this? So we use the epsilon delta method. The epsilon delta method simply starts with an epsilon. So there exists, for all epsilon greater than 0, then there exists a particular delta also greater than 0, such that if 0 is less than absolute value of x minus a less than delta, then the absolute value of f of x minus L is less than epsilon. So, there are some key components of this function we need to identify. We need to identify a, we need to identify f of x, right? We need to identify this. And of course, in this case, we need to identify our L also, this 2a plus 1. We need to identify it. So we need to identify L. So L here is 2a plus 1. F of x is 2x plus 1. So, of course, x is x. So, and what we want to do is that we will start with, so in this case, right, in this case, we have 0 less than x minus a is a here, less than delta, okay, such that absolute value of f of x, like we said, is 2x plus 1, all right, minus L. Our L here is 2a plus 1, okay, and that is absolute value of that is less than epsilon. So we want to work on this until we get x minus a in the center. So I can change this, and I have 2x plus 1 minus 2a minus 1 is less than epsilon, okay? So here, it means that we have absolute value. So plus 1 and minus 1 will go. So we have 2x minus 2a is less than epsilon. So we can factorize 2. So 2 into x minus a is equal to epsilon. This is easy peasy. So we can divide through by 2. We have absolute value of x minus a is less than epsilon over 2, basically. So in essence, this now mirrors that expression for delta. So that's absolute value of x minus a is less than delta. So what happens? So we can say that, so delta is epsilon over 2. If you like, that's half. Delta is half epsilon. So, since we can get an expression like this, we can say, therefore, for all epsilon greater than 0, there exists, we have found a delta, right? We have found a delta, which is half of epsilon. There exists a particular delta greater than 0, okay, such that 0 is less than absolute value of x minus a less than delta, and then absolute value of 2x plus 1 minus 2a plus 1 is actually less than epsilon, right? So that's the way to go about that proof. All right. So having done that, we can go back to where we are coming from. Okay. So we can go back to, I can just minimize this and go back to this. Yes. So we are back here. So we can see how this one has been done now. So it's basically that idea. So we can say that, so look at how exactly what I've done. So we want to show that for every epsilon greater than 0, there exists a delta greater than 0, such that if we have this expression, then this expression also holds. So we now have this. So if you tidy things up, it's factorized to, you end up getting epsilon over 2. So if we choose delta is to be epsilon over 2, then 0 is less than all this, and we're able to say, thus for any epsilon greater than 0, we can choose delta is epsilon over 2, and the condition is satisfied. Therefore, limit as x approaches a for 2x plus 1 is equal to 2a plus 1. That's what that's about. So for this last one, you want to check it out. So just look at the way it is and follow the rules. So it may involve some trig ratios, some trigonometric identities and everything. So just look at that and see how it ends up. Okay, so and then there are some problems to try your hands on. So prove the following using the epsilon delta approach. I'm flashing that right now. Just prove all this using the epsilon delta approach. Okay. So with this, I come to the end of this interesting video on limits of functions and continuity in the realm of real analysis. Thank you so much for listening. Let me know how helpful this video is for you. And if there's something you'd like me to try out, feel free to let me know. Okay, if you have subscribed already, thank you so much. If you haven't subscribed, of course, you want to do that right now so that you don't miss out on anything anymore. So subscribe and hit the notification bell so you can always get alerted each time a new video is released. After that, you can take it a step further. You can become a member of my channel by clicking on join, and you see 3 levels of membership, and you can choose where you want to belong, and that each one comes with a special privilege for sure, like that, as you can see when you check it. All right. So ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.